Hello students, good evening. Today our topic is current electricity. Now you must be knowing what is current. Current, as you know, it's nothing but rate of flow of charges. So for rate of flow of charges, what do we write? That is, say this is a change of charge per a unit time, del t. So we can write del q by del t. But suppose now del t is a finite time. When we go for a very small time duration, so we can write, if that is in terms of calculus, we can write del t, if it tends to 0, then del q by del t becomes what? Dq by dt. So current is nothing but dq by dt. This you know. So it is nothing but coulomb per second, and the unit we denote in ampere. Now current is flow of charge. Now what kind of charge? We haven't said that. Charge, what kind of charge? We haven't said that. Charge, as you know, it can be positive as well as negative. But what do you think? In a metallic conductor, what kind of charges will flow? Positive or negative? It will be definitely negative, because electrons, they are mobile, they are free, so they are free to move along the metallic surface. So mostly the charge carriers are electrons. But as another thing, like the protons, which are bound within the nucleus, they will be definitely not moving. But it does not mean that there are no positive charges. Or positive charges cannot be charge carriers. No. Electrons are charge carriers in the case of metallic conductors. But in the case of electrolyte, you know, it's nothing but where the charges, where that is a salt is mixed with in some chemical solution, and we have positive as well as negative ions. So positive plus negative ions. Now this positive and negative ions, they are carrying charges. So when they are moving within the electrolyte, they can also behave as charge carriers. Now for positive and negative, so when we have positive and negative charge carriers, and they are moving randomly, and if they are moving randomly, we would not get an electric current, definitely, because we are not having a net flow of charge. Suppose we apply an electric field. An electric field, you know, it's nothing but it's force per unit charge, and it is an cause which makes electric charge to move. Now if we apply an electric field, this charge carriers, positive and negative, they will be pulled or pushed according, like if it is a positive charge carrier, it will go along the electric field, and if it is a negative charge carrier, it will go away of the electric field. Now what will happen? So this positive and negative charge will go in two different directions. But what will be the current direction we'll take? Current, one thing I should have specified. Current, when I write current equals to dq by dt, this is the mathematical expression. But here the rate of flow of positive charges. The rate of flow of positive charges. So if positive charges flow in this direction, current is also in this direction. Now negative charges, if it is flowing in this direction, it means, on the contrary, you know from your previous classes that positive charges are moving in this direction only. So current comprises of both, the current component comprises of current given by the positive charges in this direction, as well as current component comprising of the negative charges flowing in this direction. So I can write this is IP plus in, where ip is a positive and in is a negative. Both are moving in the same direction and we are adding them up. Follow this. Okay, now let's come back to this atomic model. This when the electrons are moving within the metallic conductor, what is happening? Because why we are not dealing with electrolyte, though current are flowing within electrolyte as well as metallic conductors, as we mostly deal with metallic conductors, we will be mostly, we'll be continuing with the metallic conductor, this model. Now, when electrons are moving within the metallic conductor, you will see there are fixed charges. So electrons are hitting these fixed charges, so they are colliding and they are spread in all directions, and they are moving. They cannot maintain a particular direction. As after collision, they go along in various directions. So we cannot say if we don't apply an electric field. So when it is in a random motion, it means no current. So we have already said, when we give an electric field, then what happens? Then electric field, force per unit charge. Now charge of an electron is E. E is the charge of an electron. The force applied will be E. E small e is a charge of the electron, and E is the electric field, which is a vector. Force is also a vector. Now what is the acceleration gained by for this electric field? Acceleration will be definitely E divided by m, where m is the mass of the electron. Now what will happen? So we can understand, or we can think, like all the electrons will have an acceleration. Now if we go on applying this electric field indefinitely, so it means the acceleration is also applied to the electron indefinitely. It means the electron is gaining in speed and finally it can reach to infinity, which does not happen actually. So we are assuming the electron's speed is getting into infinity. It is going in infinity, but actually it is not happening. Why? Because as it is gaining the speed, it is also colliding with the immobile charges, right? And as they are colliding, and with themselves also, as they are colliding, they are moving apart. And again, as they have the force, they are moving in a separate direction, but again coming back, they're trying to move in the same direction. So because of the force, it is accelerating. Because of this collision, it is decelerating. So with this constant collision and constant acceleration and deceleration, they achieve an average speed. Which is called average velocity, because it is moving in a particular direction, average speed in a particular direction. So we call them as drift velocity. Drift velocity we represent by Vd. Now how we can relate drift velocity with this acceleration? So what we learned, Vd if drift velocity, and the acceleration gained by each electron is this. Now we define a constant which is nothing but it is called the relaxation time. It is called the relaxation time. Its order is 10 to the power minus 14 second. What is this? This time is time between two collisions. That is, if an electron is moving like this, it is hitting another electron going in another direction, and at the same time it is also accelerating, and it is hitting another immobile charge. The time between average time between two successive collision is called the relaxation time. So you can actually think that the velocity, the maximum drift velocity achieved within this relaxation time should be acceleration into that time. So Vd we can write E by m into tau. This is one of the important relationship we need to remember. Now, let us now assume how we can define electric current with the help of this drift velocity. Let us assume this is a metallic conductor which is having an area A, and say the drift velocity, the average drift velocity of the electron is Vd. Okay, now in time, say in time t, how much this electron will move? The distance moved will be Vd into t. Now Vd into t is the distance covered by the electron. Say this is the distance, Vd into t. Now what is the total volume occupied by this distance and this cross-section area? The volume will be Vd into t into the area A. Now let n is number of electrons per unit volume. N is number of electrons per unit volume. Now the volume, when an electron moves with a velocity Vd in time t through an cross-section area A, it draws a volume of this Vd into t into A. And so how many electrons will be there within this? At a time, that will be definitely, this n will be n into V, that is n Vd t into A. Now what? Now n is the total number of electrons within this volume. What is the total charge? Charge will be nothing but this n into charge of 1 electrons, that is n e Vd t into A. Now what will be the current? Current is nothing but charge by time. So if you divide by time, it will be n e Vd into A. So we can define electric current in terms of the drift velocity. That is n, number of electrons per unit volume, E is the charge of the electron, Vd is the drift velocity, and A is the cross-section area of the metallic conductor. Now we can derive another relationship from this equation. What we wrote? I equals to n e Vd into A. Now if we divide I by A, we get another thing. Current, understand, current by area, it would be, so we can see current passing through unit area, it is denoted by J and is called current density. I by A, it becomes nothing but n E into Vd. Now let us explain this current density in a little bit more detail. What we understood that is current density is I by A. Now let us say in this metallic conductor, electrons are, say electrons are moving like in this direction, so current is moving in this direction, right? This is the cross-section area, right? So current density will be I by A. But if the cross-section area is not like this, it is at an angle like this. If we take, so like if this is a conductor, if the cross-section area is like this, it's not like this, we are not taking perpendicular to the flow of the current, but it is at an angle. So what will happen? See, you definitely know that area is a vector quantity, where this vector, the vector what that is, which is perpendicular to the surface of the area, is the area vector. So we can denote this as A vector. Say this is making an angle theta with the flow of the current. Okay, so now if this is area A with this direction of the current, to get the idea how much current is flowing through unit area, definitely we need to take this area, that is, we need to take the area which is perpendicular to the flow of the current. So this area will be nothing but the cos component, the cos theta component of this area. So the current density J, I can definitely write I divided by not A but A cos theta. If we take this side, I will be J A cos theta, and in terms of vector, A is a vector quantity. Very interesting, the current density is also a vector quantity, but I is a scalar quantity. So we can see JA cos theta, it's in the form of dot product. So I can be written as J dot A. So this is another relationship where you know that current is a dot product of the current density and the area. Okay, the current density unit, what it will be, I by A, definitely it will be ampere per meter square. Okay, now I'll come to a next topic, that is on resistance. For resistance, basic knowledge you do have, that is, it is the obstruction to the flow of current, and like you we will discuss Ohm's law. Just like you also know that V equals to IR, right? So R is obstruction, that is a resistance, it is measured in ohms, all these things you know. You also know, like in a conductor, if cross section area is A, the length of the conductor is L, and the material of the conductor, the resistance is different for different materials, right? We have a quantity called rho. Rho is nothing but which is different for different materials, which is called the specific resistance. I'll discuss in more detail. Specific resistance. The relationship will be, for resistance, it is nothing but rho L by A. So the resistance of a wire is proportional. See, if specific resistance and cross section is constant, so we can say R is proportional to length. So definitely, if we take a longer wire, it will be having more resistance. If we take a thicker wire, a broader wire whose cross section area is more, the resistance is inversely proportional to the area, because it's in the denominator. You can think it more physically, like if we take a longer wire, electrons will get more obstruction to cross the wire. At the same time, if we take a thicker wire, then what will happen? Electrons will get more space to move. So if we take a thicker wire, that is more area, resistance will be less. And rho is called the specific resistance. See, from this equation, we can define specific resistance. Specific resistance can be defined as resistance per unit length, means we are making L equals to 1. So rho into 1 per unit cross section area. So area also we are making it 1. So this is 1 unit length, this is unit area of cross section. So specific resistance will be then resistance. So resistance of a conductor having unit length and unit cross section area is nothing but the specific resistance. And specific resistance depends not on the physical structure of the wire but the material of the wire. If we take good conductors, specific resistance will be low, very low in fact. If we take conductors like the nichrome wire, where we actually make the resistance wire, there the specific resistance is more. If we take bad conductors, then the specific which does not allow the current to flow, the specific resistance is very, very high. Now specific resistance, as it is dependent on the material and on the nature of the conductor, the nature of the conductor also changes with temperature, because if you increase the temperature, what will happen? The immobile charges, as we increase the temperature, what will happen? The immobile charges are not exactly immobile, they are vibrating at their mean position. So that vibration will increase, and if the vibration increases, number of collisions will increase. If number of collision increases, definitely the time taken to cross the material will be more, and means the obstruction is more, so resistance will be more. So if temperature increases, resistance usually increases. Why I said usually, I'll tell you soon. So usually what happens, if temperature increases, the resistance increases. If we denote R0 is the resistance of the wire at 0 degree centigrade, and RT is the resistance of the wire at T degree centigrade, then we can write equation RT equals to R0 1 plus alpha T, where T is the change in temperature, or I can say T is the increase in temperature in this. Alpha is called the temperature coefficient. Temperature coefficient alpha is the unit of alpha will be nothing but it will be a very small number per degree centigrade. So alpha's value is positive. So from the equation you can see, if temperature, there is a rise in temperature, I shouldn't have written increase in temperature, it should have written change in temperature, because if the change is positive, RT, that is at a higher temperature than 0, you can see that RT is more. I mean the resistance at temperature T is more than R0. If temperature is a fall in temperature from 0, right, so RT will be less. So alpha is a positive value, so which indicates that in most conductors the resistance increases with increase in temperature. Resistance increases with increase in temperature. But there are a certain kind of material which are called semiconductors. Semiconductors where the resistance decreases with temperature. That is, resistance decreases when temperature increases. There alpha, or the temperature coefficient, is negative. Okay. Now semiconductors you will study in detail in your electronics and in your modern physics chapter, but to be more precise, or I mean just to bring the point, all of you know Ohm's law. This we need not to repeat much. So Ohm's law is nothing but, that is, the potential difference is proportional to I, or vice versa. I is proportional to V. If we write an equation form in equal to form, V equals to IR, where R is constant, R is a resistance, provided the temperature and the physical parameters are all constant. Now, as V equals to IR, physical parameters are constant, this is not an absolute law followed by all conductors. The conductors which follows this are called ohmic conductors. Now see, V equals to IR, if you plot a graph, V, this is I, then V equals to IR graph, what kind of graph it will be? It will be definitely a straight line. Definitely a straight line. And you can see, if we take the slope is V del V by del I. Slope is nothing but it's giving the resistance. So in ohmic conductors, this equation is followed and we get the graph like this. But semiconductors are non-ohmic conductors, and there are other non-ohmic conductors. What we define in non-ohmic conductors, non-ohmic conductors, they will not follow a straight line. That's it. So if we plot a graph V as well as I, it will take a curve like this. So when you take a curve like this, see, the slope of this graph is a resistance. But in this graph, as it is curved, all the point slopes are different. So you can very well follow. This is one slope, this is another slope. The slope is different means definitely the resistance at this point is not equal to the resistance of this point. And as this point, the slope is more, then definitely resistance at this point will be more than the resistance at this point. So if we write R2 and this is R1, so definitely R2 will be greater than R1. And how to find this? This we cannot find just by dividing V by I. For this we need calculus. So for this, the resistance, we don't say they are static or simple resistance. We name them as dynamic resistance. And here we just do dV di. Okay. Now, for electric circuit, we basically mostly we go with ohmic conductors only, like all the conducting wires, all the devices we use, any resistance in the circuit, everything are ohmic conductors, right? There, from your previous classes, you definitely know that this symbol is used for specific resistance we include in the circuit to limit the current and some other purposes. So how many resistance, if that is this resistance, we can combine them like in two different ways. This combination you know is called the series combination. That is when the resistance they are joined like this. Joined like this means what? Let us try to understand. That is the starting point of one resistance. This is the ending point of that resistance. Suppose we take this is the resistance, right? This and this. Now if we take another resistance, the ending point of this will be connected to the starting point of this. If we take another resistance, ending point of this will be connected to the starting point of this. And finally, what will happen if we join them in a circuit? You will see all the resistance are within one path, along one path. And if you add a battery of EMF V or potential difference V, R1, R2, R3, you will see as there is only one path. So current can flow through only one path, right? And definitely you know that V will be equals to I R1 plus I R2 plus I R3. Taking I common, it would be, that is, so if we write as R equivalent, so R equivalent will be R1 plus R2 plus R3. We can continue this to infinite number of resistance. So if all the resistance are put in series, the R equivalent will be this. And definitely the numerical value of R equivalent will be equivalent to the sum of all the resistances. So definitely R equivalent will be greater than all the resistances, any resistance. Now, next comes a parallel combination. In parallel combination, what happens? The resistances all the starting point are connected together, all the ending point are connected together. And if you put a battery, the current in a parallel combination, current divides along the side. In this case, you see the potential difference across all the resistance is same. Previously in the series combination, what we have seen, the current through the resistance is same. Here potential difference across all the resistance is same. What is happening? The current is dividing into I1, I2, I3. So I is equals to I1 plus I2 plus I3. So we can write, now I1 is what? This potential difference is also V. For R1 it is V, so it is definitely V by R1. For I2 is also V, V by R2. I3 is also V, V by R3. So this I, if we say this is R equivalent, so definitely V will cancel out. So 1 by R equivalent will be equals to 1 by R1 plus 1 by R2 plus 1 by R3. That is, in this case, R equivalent, the reciprocal of R equivalent is summation of reciprocal of each individual resistance. Okay, 1 by ohm. Understand? Now, here you need to follow that the R equivalent will be less than any one resistance. Even, the smallest resistance also. The R equivalent will be smaller than the smallest resistance. You can just check with any combination. Suppose if you take, this is 1000 ohm and this is 1 ohm. So what is R equivalent? Say it is 2 ohms. What is R equivalent? R equivalent is 1 by 1000 plus 1 by 2. It is nothing but, this is 1000 only. This is 1 plus this is 500, isn't it? So now it becomes 501 by 1000. So R equivalent will be 1000 by 501. Now 1000 by 501 is less than 2, isn't it? 1000 by 500 is 2, so 1000 by 501 is less than 2. So you can test it with for any combination. You will see the R equivalent in a parallel circuit, parallel combination, is less than the smallest resistance also. So we can, for in terms of, or if you want to discuss about like what kind of circuit, what kind of resistance we'll use when we need a high value of resistance, we'll go for series combination. When we need to decrease the resistance of a circuit, we go for parallel combination. We do have specific examples to it. We'll just see. Now, before coming to any other thing, let us also try to analyze what can be the possible outcome of if cells, that is the battery cells, each cell is also connected in series and also in parallel. Now, one thing I should mention in this regard, that a cell, when we draw this, it means a cell, a particular cell. If we connect several cells, it becomes a battery. Now, in a cell, every cell is nothing but is made up of electrolyte, right? So, and this is a positive, a positive electrode. This is a negative electrode. When electrolytes are moving within this, then definitely it is also having some obstruction. The electrolyte is giving some obstruction, so it is also having an internal resistance. So every cell we can denote, every cell has an internal resistance R. Now, when this any battery, This E is called the electromotive force, which is the maximum value of potential difference it can give when no current is drawn. And R is the internal resistance. Now what happens? Suppose this cell is combined, is in an external circuit. This R is an external resistance, E is the EMF, R is the internal resistance. Now what happens when current flows through it? When current flows through it, there must be a drop across the cell, right? And because there is a drop within this one, within this internal resistance. As there is a drop within this internal resistance, the voltage that we see across the terminals is not E, but it's called V, which is the terminal voltage. And see, if current I flows, so we can write V. See, V is equal to nothing but E is the overall battery value minus, if we just take this, I R. The terminal voltage V equals to E minus I R, where R is the internal resistance. And if we try to find out current in terms of internal resistance as well as the external resistance, we can also do that. I can be written as E, see, small r and capital R, I equals to E R plus R. Now, with the help of these two equations, see, I is the current flowing, R is internal resistance, you can find out the value of R, and R will be given by R E by V minus 1. You can deduce this. So R, where R is the internal resistance. Now we are coming to this series and parallel combination of cells. Now see, if there are a number of cells in this row, if there are n number of cells, each cell having a potential difference of E and the resistance, internal resistance R, in this there is a switch. What is the total, as all the cells having EMF E are in parallel, the EMF across this is E, definitely E. But what is the internal resistance? Internal resistance of all this EMF, all these cells are in parallel. So the internal resistance will be R by, say there are m number of rows like this, R by M. So what is the total current? Current is E divided by R plus R by M, where it will become ME MR plus R. In this case, in series, this is series combination of cells, this is parallel. In series, you will see internal resistance should be very small compared to the external resistance. In this, if we need to multiply the current, then the external resistance should be very small compared to the internal resistance. Then only we can ignore this compared to this. Now, what would happen if both are combined, if series and parallel they are combined? That is, then you will see there are n cells in one row and m such rows. Then what will happen? It is NE I equals to NE divided by R. There is one resistance R plus now NE by M. So it becomes MNE divided by MR plus NE. And you can write this in the form of, with little bit of algebra, you can write MR minus N, sorry, this is NR whole square plus 2MNRR. Now if we write this as like this square term MR minus NR, this can become 0 when MR minus root of MR minus root of NR equals to 0. That is, we can write MR equals to NR or R equals to N by MR. The external resistance, if we place in this value, then what will happen? This term will become 0 and current will be maximum. So this is for maximum current. Okay. We'll now come to a very important topic, which is called, there were two very important laws proposed by Kirchhoffs called the Kirchhoffs Law. One is called the Kirchhoffs Current Law. One is called the Kirchhoffs Voltage Law. What is that? In a Kirchhoffs Current Law, it says that when there are a number of resistances placed like this, and there are a number of paths which are joined to one node, this is called one node, the current and say current are moving, say in this path the current is moving in this direction, in this path the current is coming in I2, this is I3, this is I4, whatever be the direction of the current. The current direction is not our concern. The concern is, or the Kirchhoffs Current Law, what it says, that whatever be the direction of the current, the algebraic sum of the currents at a particular point or a particular node or a particular junction, it will be 0. That is, we can say for a junction, sigma of I will be 0. That is, I1 plus I2 plus I3 plus I4 will be 0. And from where does it follow? Current is nothing but flow of charges. So it follows from conservation of flow of charge. That is, we are assuming no charge is getting accumulated. Whatever charge is coming in, the charges are going out. So the total current will be 0. And this is really helpful. We'll use in problems. The Kirchhoffs' second law is the Kirchhoffs Voltage Law. Kirchhoffs Voltage Law says that within a loop, say within a loop, there are two voltage sources, two resistance, right? Within a loop, the total potential difference will be 0. The total potential difference will be 0. And this definitely comes from the conservation of energy, because potential difference, you know, that is work done per unit charge. So when we're talking about potential difference, it is nothing but the work done is 0, means that is energy, that is conservation of energy. That is, no energy is created, nothing is destroyed. But what is the application of this? See, when suppose for this, I mean, let's see how we can find the current in this, just a simple loop like this. We don't know, say V1, V2, R1, R2, we don't know the value of V1 and V2, R1 and R2. We don't know what is the direction of the current. Let's assume the current, but we know this is only one loop, so only one current is flowing. So the current, say the current is I. What will happen? See, when we travel from, the convention is, if I take the current, if we go in the clockwise direction and the current is also going in the clockwise direction, means the way we are taking the loop and and we are going with the direction of the current, then this is a positive direction. Here now, from negative to positive, when we are coming from negative to positive within a cell, this is taken as positive. That is, we are adding the battery right here, so it is V1. Now, as we are going like this, we are going from the positive electrode, positive terminal to the negative terminal. So we are subtracting it. Now, as the current is moving through this R2, there is a potential drop. There is a potential drop. Potential drop is what? It is nothing but, this potential drop is nothing but I into this resistance, that is minus IR2, and this will be minus IR1. This will become 0. So now we can easily calculate this. So if you take I this side, IR1 plus R2 equals to V1 minus V2. So I equal to V1 minus V2 divided by R1 plus R2. You can easily verify this more simple, like V1 and V2, they are in opposite orientation, so definitely it will be V1 minus V2 divided by R1 plus R2. But this is not so simple. KVL and KCL are used in much more complex circuits. We will see. Okay. Now we have, after KVL and KCL, let us come to basic devices or the instruments we use in measuring currents. Devices or instruments. The instruments, the basic device that is used to measure current is called a galvanometer. Galvanometer, this instrument, it has a pointer. If Ig currents flows through the galvanometer, the pointer will show a deflection. The deflection will be proportional to the amount of current flowing through the galvanometer. Okay. Now this is a basic instrument which deflects, but it does not exactly measures the current. This galvanometer is a basic instrument which can be converted into an ammeter which measures currents, and a voltmeter which measures voltage. How? Let us see. Now, the galvanometer, this device, when current is moving through it, the galvanometer, as it is a device, it is definitely having a resistance. Let's name the resistance as G. Now, this, when we are using the galvanometer as an ammeter, ammeter is an instrument which measures current. When we try to measure the current within a circuit, we should not, by placing the device, the current flowing through the circuit should not change. So it means definitely the resistance of ammeter should be very, very low. How we can make this? We have just discussed that if you place a resistance very small in parallel, then the equivalent resistance becomes lesser than the smallest resistance. So an ammeter, though it is placed in series, To make an ammeter, we place a very small resistance. Say we are naming it S, as it is we are shunting it, SH. We are using this shunt resistance in parallel. Now what happens? Say for ammeter we want for the maximum value of current to be measured by this ammeter is I. But the current that will go through the galvanometer that we know is Ig, and Ig is very, very small. Now a shunt resistance is a very small resistance which will allow the flow of the other current, that is the remaining part of the current, that is I minus Ig. And we know in a parallel combination the EMF is remaining the same. So definitely we can write from this Ig into G will be equals to I minus Ig into S, where S is the shunt resistance. Ig is the current that is flowing through the galvanometer for its full deflection. I is the current that is the maximum current that we want to measure by the ammeter. G is a resistance of the galvanometer. S is a very small resistance shunt which we use to make it an ammeter. So just by the help of this equation we can find the value of shunt. Now this for ammeters. What about voltmeters? For voltmeters, it is very interesting to note, voltmeters are used to measure voltage across a certain resistance. So here also, if we connect the voltmeter, it should not alter the current that is flowing through the resistance. So we should assure that the current flowing through the voltmeter should be very, very less. So definitely the voltmeter, the resistance will be much, much higher, isn't it? So to make the resistance much, much higher, what we can do, we can attach a resistance in series with the galvanometer. So what we do, we connect a resistance R such that and we are connecting in series, so such that the current Ig is flowing through both G and R, and this whole thing is measuring the voltage that we want. So say in a voltmeter the maximum voltage we want to measure is V. So for maximum deflection what we can write, V equals to Ig G plus R. V is the maximum voltage that a voltmeter will measure. Ig is the current through the galvanometer. G is the resistance of the galvanometer. R is the series resistance. Okay, now let's come to some problems. We do have few other devices. We'll see if we can do in a later class. Let's solve some problems. See, this is a very interesting problem. In the circuit below, the current in each resistance would be, see, this is, in this circuit, see, these are 1 ohms and these are 2 volt. Initially, if you see this diagram, it will look very complex. But if you observe each of these 2 points across each of the resistance, you will see for 1 ohm, the potential difference across 1 ohm for both this is same, 2 volt. Here also it is 2 volt. Here also it is 2 volt. So as a potential difference across the resistance is 0, the answer will be there is no current flowing through the resistance. So answer will be 0 amps. Let's come to this problem. When a current of 5 milliamps is passed through a galvanometer having a coil resistance of 15 ohm, we were just discussing that. That is, it is said what? When a current of 5 milliamps, so definitely Ig will be 5 milliamps here, is passed through a galvanometer having a coil resistance of 15 ohms. So here the coil resistance means a galvanometer resistance is 15 ohm. It shows a full deflection. The value of resistance to be put in it into a voltmeter of range 0 to 10 volt. So we are making a voltmeter of range 0 to 10 volt. What will be the maximum resistance that we can use? For voltmeter, what resistance we have to use? We have to use a very high value of resistance in series. So definitely V will be equals to IG G plus R. Now this V value of V will be nothing but 10 volt. This value of V equals to 10 volt. IG is 5 milliamps, G is 15 ohm. By putting this value, you can very well find out the value of R. Okay. Just come to this problem, number 3. When a 5 volt potential difference is applied across a wire of length 0.1 meter, when a 5 volt potential difference is applied across a wire of length 0.1 meter, so V equals to 5 volt and L equals to 0.1 meter. The drift speed of electron is 25 into 10 to the power minus 4 meter per second. Vd 25. If the electron density means number of electrons per unit volume. So N equals to 8 into 10 to the power 28 per meter cube. The resistivity of the material. Now we haven't formulated or derived any relationship of resistivity with VDN and stuff, isn't it? So what we can do? See, if you remember, I equals to what? In terms of drift speed, N E AVD, where N is the electron density, E is the charge of the electron, A is the cross-section area, VD is the drift speed. Now I is what? I is the current flowing. The current flowing, so we can write I and the resistivity we need to find out, right? So V, the potential difference applied is 5. So I we can write V by resistance. V by resistance. Resistance we can write rho L by A. So it becomes VA by rho L. Now if we equate this to equation, it becomes C VA by rho L equals to NEA VD. Cross section area, it is not given in the problem, so AA cancels out. Rho is the unknown, so rho I can write rho, if it goes this side it becomes V divided by NE VD into L. So N is the electron density, it is given in the problem. E is the charge of the electron, you know, 1.6 into 10 to the power minus 19 coulomb. VD is given, L is given. So you can very well find out the resistivity. Okay. And a last problem, I don't have the time to discuss. I'll just share how we are solving this. In the circuit shown below, the current in the 1 ohm resistor is see, I'll just say how we will proceed with this kind of problems. I'll just write the equation. This is 6 volt. This is 3 ohm. This is 3 ohm. This is 1 ohm. This is 2 ohms. Now, this we need to find out. This is P and Q. We need to find out what is the current in this P and Q. We need to find out this is the circuit. To find out what is the current flowing, we will be applying Kirchhoffs both the laws, KCL as well as KVL. Say we are having two loops, loop number 1 and loop number 2. let current flowing in this is say I1. Let current flowing in this is I2. Now see, if you see this junction, we have assumed, we don't know whether these are the direction of the current I1 and I2. But if you assume like this I1 and I2, this point the current will be nothing but I1 plus I2. Now let us try to write the equation for this. This will be, see, we are going like this, so 6 minus 3I1 plus I2 minus 1 into, that is 1 into I2, it is 0. This is one equation. If we go for equation, loop 2, there what we can write, again starting from this 9 minus 2I1. Now as we are traveling the loop in this direction, but the current is in this direction, so it will be not minus, it will be plus 1 into I2. Again, this is I1, I2 is in only this part, this is again I1 only, minus 3I1 equals to 0. We are starting from this. This is I1, this is I2, yes, this is again I1 only, and this is I1 plus I2. So this is the second equation. By solving these two equations, you can find out the value of I1 and I2. And what is the question asked? What are the values of current in this each loop, each path? So we can find out. Only thing, remember, suppose the value of I or I1 or I2 comes negative. What does this mean? If it comes negative, we need to just understand the direction in which we have taken the current. The actual direction is opposite. If we have taken the current direction is this, the actual direction is this. So nothing to worry. If you by applying KCL and KVL, we can easily formulate, we can easily find out the answers of this kind of problems. Just remember, as we are going from negative to positive, we are taking EMF to be positive. For if we go like opposite, if we go from this to this, it will be negative. Now as current is in this direction, but we are traveling the loop in the opposite direction, we will add up the drop, will not minus the drop. Just apply this concepts and this law and solve more problems on current electricity. It is very much formula based and it's very mathematical. It's all numericals. So I hope you will be definitely scoring much better in current electricity in joint entrance. Thank you.